final lecture in the Teller series of interdisciplinary science. Today's lecture will be Dan Nocera, and if I read Dan's biography and all the awards and so on that he's gotten, it would take us to about 3:30. So let me just say that Dan got his PhD with Harry Gregg at Caltech, moved on to Michigan State, and then became a professor at MIT. Among the awards he's gotten are the E Prize in 2005, IAPS Award, Berghausen Prize, Harrison Howe Award, ACS Organic Award, and UN Intergovernmental blah, blah, blah. So, if you remember the last talk, we had a rather awkward experience where the next class came in and cut into our speaker's time. So I'll quit now and just remind you that there'll be a reception over in the lobby of Engineering 3, which is now Gaussy Hall, after this talk. So if you don't get your question in at the end of the seminar, you're invited to come over and talk with Dan over in Engineering 3. Thank you.
Thank you, Steve, and chemistry and applied science and Davis. You'll see Davis has a lot to do with today's talk, so I'll bring that up. That means I had to throw in extra slides, which means I took out even more other science slides. And I have to finish by like 10 of where this crazy professor comes in and we get in a fight. Which, since I come from MIT, I'm used to doing that all the time. We fight all the time at MIT. So, but even more, I want to go into. Okay, so I want to talk about personalized energy for one person. You'll understand why I'm saying for one. I can't explain this except that this is a drawing done by a graduate student of mine who I didn't even realize was very famous in Japan because of this character, and he runs a major business out of my lap, which I only found out about recently. So I therefore had him do this for an awards address I had to give, and you can see I'm going to destroy the grid with her or him. I can't still figure that out. With the sun and photosynthesis for a single person. And so here's the big difference is the way we're going to do energy is not the way you guys do it in the legacy world, which is build one big thing for everybody. We're going to build one thing for a person. And then the way you scale, so you always worry about scale up. How do I go from a laboratory bench to a big system? You don't need to here. You go from a laboratory bench to a laboratory bench, a little prototype, get it right, and then manufacture the heck out of it. And that's how you get to 6 billion. I'm not going to go through all this because I practically have no time to. Just to tell you that we use 14 terawatts, so you're burning a 1 trillion watt light bulb. That's power, not energy, energy per unit time, joules per second. And then you're going to 16 terawatts in the next 40 years. And you've probably heard these numbers now. That's a lot of energy. So you can read some of all the biomass can only get you to 5 to 7. 8 is for every 1.5 days building a nuclear power plant. Okay. Solar has a lot of energy. It's just too expensive. So all these numbers pan out. You can go read these papers. Now, the question you can ask is, if we need 16 terawatts, and you can see how hard it is to get at these numbers, why? And there's one thing you need to remember. There's a paper I published with my sometimes friend and sometimes nemesis, Nate Lewis, and it was a PNAS paper. And when Nate and I did that calculation, people use this all the time now, but what they do, and I've been to many seminars of people who use these numbers, they get to this whole gig at the end where they say, oh, we just need to conserve a lot, and we'll be okay. And they're right, you need to conserve a lot, because when Nate and I did these calculations saying you're going to have to get to 16 terawatts in 2050, we assumed that you in the legacy world would save every bit of energy you use today. So what we're saying is by 2050, you're going to save 14 terawatts, and you're still going to need 16. If you don't do that, then you need 30 terawatts. All right, so saving isn't enough conservation, but you better do it. So all the energy efficiency stuff you hear about, and about science and engineering, it has to happen, and you still need 16 terawatts. And then why is that the case? So I'm going to just work the problem backwards, and this is how we went off on this line of research, is we said that the case? And it's because there's 6 billion new energy users coming. So there's 3 billion people to be born in the next 40 years, and there's 3 billion low energy users. So that's 6 billion basically new energy users. And it's them who's driving this extra 16 terawatts if you save 14 terawatts. And so then the question becomes, if that's the case, and these are all my biases, so this is just opinions, you don't have to agree with me, but that is then I should do energy and science for the future for poor people or people from the non-legacy world, not you guys. And I'll assume there's lots of other people doing science for you, which there are, because that's how funding agencies act. And they'll take care of you and give you enough money, hopefully, to save 16 terawatts or 14 terawatts. And so I think the key to getting carbon neutral energy and greenhouse gases is to address the 6 billion non-energy users. And if you do that, here's a big difference from how you guys do science and I do science. We always like having a very efficient system that's beautiful, so it gets into science or nature, and that's exactly what you don't need for the poor. Because whenever you go to super high efficiency, it always comes with a lot of cost. So the inverse is to say cost is what matters first, and then I'll worry about efficiency later, if I'm going to get energy to the non-legacy world. And that means you can't do what the Department of Energy always does, which is basically not very inventive. What they do is they take big energy systems that are known today. Remember, all of them have been designed for the legacy world. Then they try to downscale it. And when you downscale big things, which are defined to be efficient or designed to be efficient at large scale, when you finally downsize it, they never scale with cost. So if I take a thing that goes to 1,000 and I go to 1, I can't divide by 1,000 because there's a whole bunch of what's called balance of systems cost around the thing for 1,000. And when I downscale to 1, I still need the balance of systems, and that never scales. So the imperative, so you could ask, so guys like Al Gore who say, we already have the technology, take it off the shelf, they're wrong. We have technology to take off the shelf that will never scale, especially for the poor. So that's why you need science and engineering, because you have to actually start with a blank piece of paper and say, and I'm going to show you this today, what can I make from the ground up to get rid of the balance of systems costs? That's a different question. I'll show you today. This is Eric Morris, who I just learned from Susan's from UCLA. And Eric Morris is in the transportation department. And if you look back here, when I was, oh boy, if I was back here, look, to get 8 terawatts, you need to build 1.5 nuclear power plant every 1.5 days forever to get to 8 terawatts, right? Because I'll do only one calculation for you, because I do lots of calculations. A nuclear power plant puts out a gigawatt. If I want 8 terawatts divided by a gigawatt's 8,000. I need it in 40 years. 8,000 divided by 40 is 200. That's 200 power plants a year. There's 365 days in a year. That's around every 1.5 days. Why am I saying forever? Because you can only build a nuclear power plant for around 50 years, and then you got to decommission it. So the one you built 1.5 days from now, I got to get ready to decommission in 50 years and start rebuilding a new one. Okay? So all these calculations are easy to do when you start thinking about it. So you see those numbers, and they're huge amounts of energy. All right? And so I'm extrapolating to the future. Well, I just want you to know that that's been done before. So in 1898, delegates from across the globe gathered in New York City because they were driven to desperation by force majeure. And they did exactly what I did. I'm saying I need 16 terawatts in the future because there's 3 billion new people and there's 3 billion new energy users. We use this much energy now. Let's scale forward. You need 16 terawatts. So these guys did the same thing. They said there's this many horses, but not everybody has one, but society's progressing, so by 1950, everybody's going to have a horse buggy, and we know how much manure comes out of a horse, and so I can weigh that, and when I then scale up to 1950, I'm just going to 2050, we'll see how much horse manure there is. And the situation was dire. In 1895, the Times of London estimated that about 1950, every City would be 9 feet deep in water. And then in New York City, they decided that by 1930, horse droppings would rise to Manhattan's third-story windows. This was the first global civil engineering conference ever. I want you to know that. And it was in New York City. And no possible solution could be devised. So that's the key. And the reason is they could only see a world that was transportation driven by horses who had horse manure. What does science do? Science takes what you think you know, and then we invent something and create something, and then all of a sudden that's what's called a paradigm shift, right? So the paradigm shift for this conference was the automobile. And when that came on board, all of a sudden this problem went away. So that's what scientists do. That's what we need to do for energy. When I do all those calculations with Nate, that's just telling you this is where we are now, and now I'm extrapolating forward, and I'm giving you no room for a paradigm shift to make it go away. All right. So the point, if anything, you want to realize about science and technology is that when everything seems dire, like this energy situation, shift happens. I worked hard for that. I really did work hard for that. So shift happens, and so I'm going to tell you about a little shift today, all right? And we're going to go through that. And my argument is it's going to be shift for the poor, all right? That's where I really think you need to do business. So I told you we have lots of solar energy. It's only 0.1% of the market. It really is. And a lot of people say it's because PVs, photovoltaics are too expensive, photovoltaic, and then they assume photovoltaic materials are too expensive. Let me tell you how crazy we are. So I'm doing an MIT solar study for MIT with John Deutsch, and I run the technology part, so I've gotten really into analyzing this stuff. A solar panel that you buy is very expensive. That's why we don't use it supposedly. It turns out that the module cost, just building the module, is 48%. The installation cost with inverter is 29%. Maintenance is 21%. Guess how much the cost of the photovoltaic material is? 3%. So if you want to make photovoltaics cheaper, the last thing you should do is go in, which is every MRS conference, and make a cheap solar PV. Who cares? It's only 3% of the cost, right? Does that mean you don't do research? No. But you ask a different question. You don't want a cheap and inexpensive PV, because who cares? It's 3%. You want to go and invent something that allows you to get rid of the module cost, and that brings up different science challenges. So today, I'm going to tell you that I don't think it's the PV cost that's important. I think it's the storage of solar energy, so you can use it 24/7. To store solar energy costs around $12,000 per kilowatt, and that's because of the big balance of systems costs. And so a few years ago we said, why is there a big balance of systems cost? I'll show you today why that's the case. That costs a lot of money to make sure the catalyst doesn't die. And we said, what piece of science can we do to get rid of that problem so I don't have a large balance of systems and we can get really cheap? Right? It's a different question. So that's what I want to impress upon you today, and we thought it was all about storage. And the reason is this is an output from the Tucson Electric Power Company. You should go and look at them if you want any real-life data. Tucson Electric Power runs the biggest photovoltaic arrays in the United States and the biggest wind farms, and they're all run by engineers, and they've been collecting data for the last 20 years. So this is a midday in June in 2004, where every minute they collected from a 4.5 megawatt solar array the output, and you can see the sun comes up, then clouds, sun goes down. Here's your energy use that they have to deal with on a day, and you can see that curve is mismatched, so you need storage here. And this isn't zero. Remember, this is still at night. You still need that 4,000 megawatts of energy. So storage is really the key for solar, wind, the whole gamut, because you need energy 24/7. If if you start thinking about storage, you can then say, all right, what are ways to store energy? So I'm going to just lead you through our little discovery path. So this is what we did. You can compress air. PV can shine during the day. You can take some of the electricity from the photovoltaic, basically run a turbine backwards compressor, and put the air in the ground. Under pressure, the sun goes down, run it back up, run the turbine, get electricity out during the day. It turns out compressed air stores 0.5 megajoules per kilogram weight of material. I could pump water uphill during the day with the solar PV output. At night, let it come back through a hydroelectric turbine. That only is 0.001 megajoules per kilogram per 100-meter dam, because that's mgh, mass, gravitational constant times height. That's potential energy. Capacitors, 0.02. With advances in nanoscience, this has gone up 1 order of magnitude to 0.1 megajoules per kilogram. The godsend of the future of energy, batteries, they're just as bad. They're only 0.1 to 0.5 megajoules per kilogram. And that's never going to get better, because we're chemists, or at least I am. I know it, because you got to put an electron on a metal. I got to put another electron on a metal. I got to put another electron on a metal. So unless I can compress matter and not have it weigh more, I can never make the energy density of batteries go up. There's a big misconception in the community. All the research done on batteries isn't energy density, it's power density, energy per unit time, which is important for the transportation sector, but not for large-scale energy storage, because you can't store much energy in a battery. And all the dumb people who have companies who use Google to hire consulting firms at hundreds of thousands of dollars can't do this simple calculation. Understand that, okay? I just saved you $100,000 if you're going to start a new company. Where do you store a lot of energy? It's in bonds, chemical fuels. In case you haven't figured it out, you did, because batteries and capacitors and all this stuff predated fuels 100 years ago. You went with fuels. Let's do the experiment now. I got to store electrons. Here's an electron. Here's an electron. Notice I put it upside down, and I pair it, and that makes a bond. And if you look at the volume of a bond versus the volume of a solid state material, that's where the energy density scales precisely. This is freshman chemistry. And all these complicated things. So bonds will always be the place. It will never change where you store as much energy. That's why you use it. Now, I have this listed this way because it's in energy density, and you could just say, if you ever want to take me out, no, Sarah, I don't like energy density. I'm going to choose a different parameter, and I can reorder everything. So I have to justify why I like energy density. Here's my latest. My students hate me now because I don't do any science. I sit around Google making plots like this. I just want you to understand. So this is the manufacturing curve from manufacturing engineering. And all I did is I literally went on to Google and I said, how many Boeing 777s did they make in 2006? It turns out they made 75. How much did they cost and how much did they weigh? And then I put weight, price per pound versus number. There's etching tools. They look different than an airplane. There's a machine tool. There's an automobile. They're all very different looking, but I have them on the same curve. That means I have a relationship. And the relationship simply is this much. If you want to make something cheap, make it light. I can't ever get, this is also interesting. I don't care what you do for high throughput manufacturing, you will never be less than $10 per pound. That's what this is telling me. So I don't care how sophisticated it is. Whether it's a Boeing 777 or, this is the truth, a fast food hamburger from McDonald's, the quarter pounder, I called them and I weighed it out per pound, and I know how much they make. That means I've related a Boeing 777 to a hamburger. That means you do not ignore this. Okay? So listen, I want to get energy systems to the core. The last thing I want to do, even if I'm at $10 a pound, is make energy systems the way I do for you. Because with you guys, I build one thing, it's super heavy. Because it's super heavy, even if I'm at $10 per pound, the system ends up way up there. So it costs a tremendous amount of money to make. Typical power plant in the US is 1 to 4 billion. And then because you guys have money though, I can make money because I can recover my costs over the next few years by charging you and then make a profit. But poor people can't afford to do this. So you can't be up here doing this, which is you, the legacy world. For the poor, these 6 billion people, you basically have to become the fast food equivalent of energy. That brings up different science challenges. Okay? I should add, for people who don't like this doesn't work for Intel chips. It does not work for pharma. It does not work for commodity chemicals. Right? But that's not how you build energy systems. You build energy systems like this. This is just heavy-duty manufacturing. So that's why this curve was very powerful to us a few years ago. And we said, what science do we now need to do to make sure we could do high-throughput manufacturing and do solar energy storage? And it was based off of this Google curve. Okay, so that explains why I'm putting such a premium on weight, because weight indirectly scales with cost, and that's why I only care about energy density as a first cut in the energy problem. And then I told you your society figured this out, and the nice thing is nature did too. Remember, nature has membranes, and it does store electrons in cofactors, battery. It stores protons across membranes, capacitor. It does it all the time, but in a transitory way. When it's only doing that for a short period of time, at the end of the day, every cycle ends with the proton and electron stored in a chemical bond. And then when you release it, you go back through the capacitor battery. But everything in nature is stored at the end of the day in a chemical bond in a fuel. So what's the world's expert at doing solar energy storage? And that's, I'm getting the right one already. That's photosynthesis. So light plus water plus CO2 gives you sugar and O2. The one thing most people don't remember about photosynthesis is there's no energy storage in the Calvin cycle, the sugar part. Most people get that confused. All the energy storage in photosynthesis comes up front in water splitting. And if this, I like this, delta E is the normalized energy, right? Because it's delta G equals minus NF delta E, and that's just the number of electrons. So the true value of energy content is always in delta E. And this is pretty neat. If you take sugar and burn it with O2, you get 1.24 volts of energy. If you take hydrogen and burn it with O2, you get 1.23 volts of energy. You're only getting 0.01 volt in delta E out of sugar versus water. So what that's saying is all the energy storage in this reaction actually is coming from the water splitting. Nature has the CO2, and we shouldn't forget this, as a hydrogen carrier. That's all it is. It's just simply a hydrogen carrier. It's not storing energy. So when you eat sugar and then you break it back down, what you're doing in your body is getting it back to H2, which is NADPH, plus O2, and then cytochrome C oxidase, your fuel cell is combining those 4 protons and those 4 electrons with O2 to give you water and release the energy. The sugar part, to get down there, you practically got no energy out of it. You're just releasing the hydrogen from the sugar. That's it. Okay? So if you want to do this simply, solar energy storage in terms of photosynthesis, just worry about this piece up front. Now, I gave you some big, big numbers. Let me show you why nature chose water. So here's water splitting. Again, freshman chemistry, that's 237 kilojoules per mole. I can take 1 liter of water, that's 1,000 cc's, 1,000 grams. So in 1 liter of water, then if I work this out, I get 13 megajoules I can store. There's the MIT swimming pool, okay? Remember, I needed 16 terawatts of carbon-free energy. 5 to 7, all the biomass, 8 for nuclear power plants every 1.5 days forever. If I could take a solar input and split water to hydrogen and oxygen globally per second, because this is energy and now I got to put it into a power. So if I could take the equivalent of just 1 Olympic-sized swimming pool globally per second to hydrogen and oxygen, 43 terawatts. Okay? So that's your out for this energy problem. Right? This is the paradigm shift. This is the shift happening. If I can take and figure out technologies that in an inexpensive way, so that's the key, inexpensively, can take sunlight and take only 1/3 the MIT swimming pool, the hydrogen and oxygen per second. So you'll all be doing your own little bottles of water, and I just have to add it up to globally, to 1/3 the MIT swimming pool. You have 16 terawatts of carbon-free energy using sun. So that was very compelling to us, and that was what we felt a few years ago was our out of this energy problem. And I'm not going to do it centrally and distribute it. I'm going to do it for each one of you and then manufacture the heck out of it. So you all can take one bottle and we can add up per second to 1/3 the MIT swimming pool. If you put full system efficiency in, that's for 100% system efficiency. That number works. It turns out today, total full system efficiency is 30%, so it's one MIT swimming pool. Who cares? Okay. So that should give you hope. You should also know a lot of scientists get angry at me because of my discovery I'm about to tell you, and then I say things like, we can do this, and then I get really mean emails from Nobel Prize winners, National Academy members saying, you keep selling. Nocera, we did this in the 70s, we didn't deliver, and then we lost the faith of the American public. So here's my response, which I'm suggesting young students do not have this level of diplomacy. When they write to me and say, we did this in the 70s, it didn't work out, and now you're doing the same and you're selling it and you're going to lose it, I just simply write, well, maybe you guys suck and I don't. So that don't do that. But that is my standard email. So that's number one. But number two, what they should probably remember to tell people is, I can already do this. So if you guys want, we can get on Google now, and I can buy you an 8 megawatt solar array. I can feed it to a commercial electrolyzer at $12,000 per kilowatt. I can store it in a tank outside, and I can send it to a fuel cell for $4,000 per kilowatt, and I can actually do what I said. The problem is, for the average American home of 30 kilowatt hours a day, it costs $85,000. You'll then go, so we can do it. So the one thing none of my science colleagues remember is, since 1970, we've actually invented all the technologies to do it. It's just too expensive. So that's the next lesson is, nothing I'm going to tell you can't be done. It's just too expensive. So the question is, how do you do science to make it less expensive? I'm not promising them anything. It's known of it. Okay? But not inexpensive enough to want you to use it. Certainly not for the poor, and it's not fast food energy. So those are all the challenges. I'm just trying to frame the problem so you don't get confused about what I'm saying. So what I would like to do is emulate photosynthesis cheaply. But this is a tough job. People have been trying to do this for a long time. Here's a paper from 1912, and if you read those words, if I didn't tell you it was 1912, Chimichon was the first photochemist, by the way. He was from Bologna. He was an Italian scientist who only did photoreactions in beakers on the top of a roof in Bologna. Vincenzo Balzani is now the head of the Chimichon Institute. And if the reaction didn't go, he just threw it out. He wasn't interested in studying it, all right? So he was a real solar photochemist. And he said, in 1912, in science, if our nervous civilization based on coal and oil could be one, followed by using solar energy, that would be nice for us. And if we could fix solar energy through suitable photochemical reaction, new compounds master the photochemical process hitherto have been the guard secret of plants. So he figured out we needed to do artificial photosynthesis and the world would be better, we could get rid of coal and oil. 1912. If I didn't put that there, it still applies today. So that's scientists. But even Jimmy Stewart, in 1938, in the movie You Can't Take It With You, had also figured it out. So I'm going to show you a little film clip for 2 minutes. Instead of Jimmy Stewart is trying to woo this woman on a park bench, and he starts explaining her this little film clip. So listen to it carefully and think about the challenge I'm talking about, what he's saying. That's number one. Then number two, what I want you to think about is forget Jimmy Stewart and the woman. Just think of Dave Britt talking to Anne in a park. Now listen to these words. And this is literally how Britt proposed to
was another guy, and I had an idea. Mind if I talk about myself?
If you don't, that'll do it.
Well, this guy and I had this idea. We wanted to find out what made the grass grow green. Now that sounds silly, but I think it's the biggest research problem in the world today, and I'll tell you why. Because there's a tiny little engine in the green of this grass and in the green of the trees that has the mysterious gift of being able to take energy from the rays of the sun and store it up. You see, that's how the heat and power and coal and oil and wood is stored up. Well, we thought if we could find the secret of all those millions of little engines in this green stuff, we could make big ones. And then we could take all the power we could ever need right from the sun's rays, you see.
That's wonderful. I never knew that.
Yeah. We worked on it, worked. Day and night we got so excited we forgot to sleep. If we make just one little discovery, we'll walk on air for days.
Yeah. And what?
Well, we left school. Now he's selling automobiles. I'm in some strange thing called banking.
He said, I'm in some strange thing called banking. Poor Jimmy. So because he couldn't make that one little discovery, okay? So I'm going to tell you about a little discovery we made. And the big key here was to run the reaction out of a glass of water. So to do the water splitting. And here's now the back challenge. Because I told you that there's big balance of systems cost for water splitting, and there is. You can get really cheap metal oxides. It's been known for 100 years that split water to O2 and leave 4 protons and electrons behind. So you can make into hydrogen later. The problem is that when you make split water, you make protons. If you're in neutral water, that's what this glass of water is, the best base isn't water, because if I put a proton on H2O, I make H3O+, concentrated acid. So the best base is the oxide. So you put a proton on the oxide, and from freshman chemistry, acid plus base makes neutral compounds, and you dissolve your oxide. That's a 100-year-old problem. It's called corrosion. So the way that's always been avoided is you don't run this reaction in a glass of water. You run it in 14 molar base. So when you make the acid, the protons go to the base. Now watch how this balance of systems gets in here. Now on the concentrated base is a sponge. CO2 plus base makes carbonates. That crudds up the electrolyzer. So you have to hermetically seal it. And if any base sees any metal part of the electrolyzer, it corrodes it. So you have to engineer the electrolyzer not to corrode. And so all of a sudden, you take what is a simple reaction that's already known with given compounds, and you're at $12,000 per kilogram because of the balance of systems to run water splitting in very harsh environment. So what we said is I could get rid of all that balance of systems costs if we could run it in water, but then we know we're going to have corrosion. So now I'm just working backwards, and just literally how we thought. So what we said is then what we need to do is figure out how to prevent corrosion. It's that simple. All right? And if I could do that, I could run out of a glass of water and be cheap. So that was just our thought pattern here. And to do that, we went to photosystem 2, because here you have, and we actually, I remembered this, it was in 2007, in December, and we had what was known as an MIT group therapy session, called a group meeting. And I remember just going kind of crazy on my group because we were making these ruthenium oxide catalysts. Everything was expensive. And we would get for 100 turnovers, publish a JAX paper. Yay. And we would go to 1,000 turnovers, publish the next JAX paper. Sometimes we would only go to 1,100, but it was still bigger than the other one, publish a JAX paper. Then you write your renewal and life seemed happy, but it's 1,000 turnovers. You know how much a bubble of water? Matter of fact, some of the 1,000 turnovers of O2, you can't even see the bubble. Right, so that's the problem. And so what we said is what are our biases of how we do science versus nature? And here's what we came up with. The first thing is, and there's, for the experts in the audience, you know there's a little controversy over what the structure is. It really, it's is this over here and there. The first, and by the way, these are all the crystal people, and the first person to get this right was sitting here right on my right paper using EPR, right? With the dangler, so that's the dangler. So it's this cluster. The beauty of this is, look at it. We love complexity in science. It's manganese, 4O4 calcium. So for an inorganic chemist, that's a rock. That's what rocks are, right? So you look at all this, but the oxygen, the thing that's splitting water to O2, that's the machine in photosynthesis, is a piece of rock. And then this is the one we couldn't get our heads around. It literally took us hours to come to the conclusion in this box. Because in inorganic chemistry, you build stable things, and then they begin decomposing. And then what you do is you say, all right, that hydrogen bond got nailed. Let's go put fluorine there. The ligand's falling off. Let's make it more coordinating. That's what we always do. You try to make it more and more stable. And the thing about nature is it doesn't. The way this works is it will get oxidation of this D1 barrel protein. It actually removes the protein. When it removes this D1 barrel protein, this thing just falls apart. And then it starts from sulfate in water, makes a cysteine, sets up a long biosynthetic pathway, remakes D1, snaps it in, and then this piece of rock self-assembles. And it's doing it depending on organisms, every 30 minutes to an hour and a half. So nature never did what my entire field tries to do, which is make something stable. It said, let's have something be unstable, but put all our work into repairing something. And then if you can do that, we thought that would be good, because if we're going to do these conditions, which that blue box said what I already told you was low balance of system, then I could repair things that go wrong for a low balance of systems price. The second lesson we had was a bunch of work we had done for years. We never tried to study water splitting up front. We actually did the easier reaction thermodynamically, because water splitting is uphill, so I need to have a photon input. We did the fuel cell reaction, O2 plus 4 electrons and 4 protons to go downhill. What we learned, and we made a bunch of macrocycles, I don't want to get into all the details, and we could put 2 cobalts in them. What we learned is, first, that late metals over here are good because you don't make strong metal oxo bonds. That's something Harry Gray talked about maybe when he was here. It's called the oxo barrier. So you can't make strong oxos. But the other cool thing we realized here was the timing of protons and electrons and LO bond activation. So it turned out the folklore was you needed 2 metals to get to water, which is the fuel cell reaction. If you had 1, you went to peroxide. So therefore you needed not 1 metal, which gives you 2, but 2 metals. 2 times 2 gives you 4. The problem was, what we found is sometimes when we had 2 metals, we would still get peroxide. Sometimes we would get water. And then in some of the systems we made a new class of compounds called hangman porphyrins where there's no cobalt. They were the best at making O2. And what we figured out was right here. And that was you have to time protons and electrons properly. So when you put the oxygen in the cobalt-2,3 to make superoxide, if this is basic enough, and that's what this other cobalt system is doing, is just adjusting the pKa of the superoxide, I'll add a proton. If I add a proton here, it would drive a 2-electron reaction. We were able to measure all of this. And when we added the second electron, it's on the 3rd electron with the LO bond is. If the thing wasn't basic enough, then what you would do is not add a proton, and then you would add another electron and get peroxide. Right? So this is this issue of timing protons with electrons, proton coupled ET. The 3rd electron breaks the LO bond, so it's going to be the 3rd hole in a PCET step that makes the LO bond. And then finally, I have a big collaboration with a colleague of mine at MIT, Joanne Stubby, who studies the enzyme in your body called ribonucleotide reductase, which takes RNA to DNA base pair at a time before transcription. And that's done by tyrosine radicals. Our contribution to that field in the last few years is we figured out how to make RNR photoactive, so we can come in with a laser and excite RNR, and then set off its chemistry. And the way we do that is we make tyrosine radicals. And that works, so here's one of, we usually put this on a long peptide and then use different biomethods to incorporate that into R&R. The point here for energy issue is we could never make the tyrosine radical if we just put it in water. And the reason is when I pull an electron out of tyrosine, the proton has to get lost and you can't put it on water. So what Steve figured out, Reese, is if you had phosphate, you could do a long electron transfer, because electrons are delocalized, so they spread out over long distances. I could couple that to a short proton transfer. It's more classical. The quantum tunneling rate is much tinier. And so by doing this, I can then match the two length scales, long electron tunneling to short proton tunneling, and I can couple them, and I can activate that oxygen. So I'm doing this quickly, but we figured out from a whole bunch of different studies, use cobalt. Of the 4 holes needed, the third one's critical for water activation. Use phosphate to accept protons from water. Activate oxygen by PCET with phosphate. And then don't try to make a stable catalyst, repair an unstable one. Now, why is that important? If we look, we were going to use cobalt. If you use cobalt, there's no escaping. You can't get the cobalt 5 easily. So there's no escaping cobalt 2. So if I need 4 holes. I need 4 holes. So if I go from cobalt 2 to 4, I get 2. With 2 of them, I can get 4. After I make O2, I return to cobalt 2. Now let me tell you how dumb we had been. I mean, really stupid. I wasn't listening to myself even when I teach freshman chemistry. So when I teach freshman chemistry, this is a D5 metal, this is a D6 metal. It's cobalt, it's low spin, T2G, EG. You know, the old Hans Bethe ligand field here. EG is an orbital, is metal ligand antibonding. When you populate it, ligands dissociate, all right? Well, cobalt 3 and 4 are low spin. Cobalt 2 is D7, it's high spin. You put electrons there. It's impossible to make a ligand, by definition from ligand field theory, to make a ligand that stabilizes cobalt 3 and 4 that will also be okay for cobalt 2, by definition. And that's what we were doing. So I could finally make ligands that stayed on cobalt 2, but then the ligand shouldn't have been there. So for me to get the electron in from 4 down to 2, I had to push extra hard. That gives overpotential, and that gives inefficiency. The solution of this problem came from this man right here, because this paper we keyed in on. And at this university, this was just when you came here. So it was known from Professor Casey's studies that cobalt-3 oxides were really stable. This comes out of this paper. But cobalt-2 oxides were really unstable. They dissolve quickly. And it's basically this ligand field argument that's driving that chemistry in oxides. And we were going to be figuring we would be making oxides. So what we figured is we'll get this instability at cobalt-2, but we'll use the cobalt-3 state as our re-entry point to remake the catalyst and repair it. So that's what we decided. And for various reasons, which I won't go into, we knew phosphate could carry that chemistry. So this guy, Matt Cannon, took a glass of water, literally, put cobalt in it, put phosphate in it in the right way. Cobalt-2, just like Professor Casey predicted, was really soluble because it's ligand exchange, totally soluble. But as soon as we oxidize cobalt-2 to 3, then the phosphate drives an equilibrium. This material comes out on the electrode, and as that material forms, you see water being split to O2. And this is at 10 milliamps per centimeter squared. Keep that number in mind. I make 4 protons and 4 electrons. They get recombined over here, and I'm not showing it to make hydrogen. So we're doing water splitting. I'll just mention this week, we've done it also with a totally different system using nickel and borate. And it works really well too, maybe even better than the cobalt phosphate. But it has all the same concepts that I'm about to tell you. So you could say, what's the big deal? When I was in grade school, I used 2 platinum electrodes. The teacher did, and he split water to oxygen and hydrogen. Remember that? They turned on the current. So the first problem is platinum is expensive. So if you're going to go to the poor and you're going to do mass distribution, you shouldn't use platinum. But the other thing is platinum isn't good at splitting O2. So what the teacher does in an oxidation, the energy of the whole is a reactant. So the teacher kept, what you weren't watching is the teacher kept turning up the potential so you could see lots of bubbles. By turning up the potential, I make the activation barrier smaller, so it goes faster. The cool thing about this cobalt catalyst is for a given overpotential, so this is potential past the thermodynamic minimum. For a given overpotential, the cobalt catalyst at any overpotential is 3 orders of magnitude better than platinum. So not only is it cheaper, it's 1,000 times better, right, or faster. The next thing is, what is it? You can actually just take the catalyst, we take Mylar, we sputter ITO on it, and then we can actually send electricity to the ITO. In the Mylar, we can go to Stanford, have the beam come through the X-ray absorption spectroscopy. So we can have the synchrotron beam come through, and we can do the structure in real time. The red spectrum is the catalyst. The blue spectrum is a conventional metal oxide, like cobalt dioxide. And we realized immediately it wasn't a conventional material. And usually what you get are these what are called focusing effects. You see, if you're in a solid state material, there's always a next near neighbor interaction. And if you look at this red spectrum, that is minimized, number one. Number two, which I won't go into, there's only 2 distances of significance, cobalt dioxide, cobalt, cobalt. And finally, this XF spectrum is almost an overlay to the manganese-oxygen evolving complex in photosynthesis. So we had a good feeling this was molecular. While we were studying this, Holger Dow in Germany came up with a structure which was, we were really happy. I was happy for 2 reasons, even though I got scooped, kind of. One is, it's a molecule, which is what we thought, and so he has it as an edge-sharing cubing. Number 2, he's a physicist. Holger can't boil water, man. And he was able to make my catalyst. So we always felt this thing had legs, because if you can have a physicist make it, then anybody can make it. So we were very happy about that. We've been working away while the catalyst is in operation. We've submitted this to JAX. I just want to say we're not that different from Holger. If I take that cobalt and move it there, and I take this cobalt and move it there, I get that structure. And if I take that structure and rotate it, you get that structure. So even though that looks a lot different than that, it is. This is, for an inorganic chemist, this is called corner sharing octahedra. This is actually edge sharing octahedra. And this is a common structure in metal oxides. So what we've done is we've made a molecular piece of a layered oxide in effect. Okay, that's number 1. And the importance about that is we have lots of edges. I'll show you where the edges mean a lot. And a lot of times you hear heterogeneous or solid state chemists say that. They say all the reactivity happens at the edges. I'll show you in a chemical reason why the edges are so important. If you take this material, and we have, and you extend it to infinity and oxidize it up to cold, you put potential on it, guess what? It doesn't oxidize water, it just simply intercalates water and swells the layers. So the edges are really important. Here at Davis, work here has shown that the active state, so like I sort of inferred, that the active catalyst hits a cobalt-4. This just came out in JAX, so that's what Greg has done and Dave Britt's group using EPR. We can run the catalyst to the oxidation potential and then freeze it and take the spectrum. So that's a classic cobalt-4 spectrum, and we're working a lot on that. Yogi in my group with Mircha using electrochemistry, looking at activity as a function of pH and overpotential, that determined that it's a 1 electron pre-equilibrium and a 1 proton inverse dependence, and that's perfect for, it dovetails nicely with what Dave has seen and Greg, and that is that we have a PCET, just like I told you. We can see the proton gets coupled to phosphate. We take cobalt 3 to 4, just like Steve did. And then once we get to cobalt 4, we have the rate determining step for oxygen release. And I won't go into this, but using labeling experiments, we're pretty sure that the reaction is that the pre-equilibrium is this one right here, where we take this somewhere sure of at least this type of stoichiometry is we can make the cluster out of O18 oxygens. We can put it in O16 water, and the first burst of O2 is a 34 oxygen, which is 1 oxygen from water and 1 from the cluster. This thing is self-healing, like I told you, and like Professor Casey, using his work, we knew would happen. So when you have a potential on this, it's stable. As soon as you turn the potential off, you make cobalt-2. I told you cobalt-2 is exchangeable. When we build this cluster out of 57 cobalt, radioactive cobalt, and then, this is an easy experiment, put it in regular water and just look for radioactivity in the water. We can get the equilibrium constant. So here's cobalt showing up. As soon as we put a potential on it, it goes back in. Off, in. What that allows us to do, and this is, so that's showing the healing, and we can do it for P32 and get the phosphate exchange as well. That's much faster than the cobalt. The cobalt's coming out of this core slowly. The beauty of it is any commercial catalyst that's known, these are nickel oxide catalysts and electrolyzers, if you don't use pure 18 mega ohm distilled water catalyst, the whole electrolyzer dies. You're $12,000 per kilowatt gone. You have to buy a whole new inner workings of the system. This catalyst, because it's always breaking down and reforming, you're in water, so you can't make any passivating oxide layer, number one. And the other thing is, because it's breaking down and forming, we never form biofilms. So we've been able to run this catalyst, it's now up to 4 months out of the Charles River, okay? Because you can't make a biofilm, so we don't need pure water. We can run it out of wastewater, so we can run it out of human wastewater from that. I'll tell you why that's very important in a second, right? And it's all because of the self-healing or anti-corrosion, because I can use any water source. So this is what we figured out so far. You bring this up to the cobalt 3,4 state at the 4,4. We don't know the mechanism yet. That's stuff we're looking at here at Davis, and we're doing at MIT. You then make the OO bond, the O2 falls out, you get the cobalt-2, some of the cobalt-2 comes out, but then we take advantage of the Casey work and take cobalt-3 with phosphate, and this cluster self-assembles. So the catalytic cycle is this, while the normal catalytic cycle would be that. If you listen to freshman chemistry, catalysts aren't used up in reactions. This one is, because it's decomposing, so it's used up. So the real catalyst is this thing plus the 200 millivolt overpotential we have to supply the system to do the repair. Okay? Because it is the first self-healing catalyst, it doesn't even fit the convention of what a catalyst is. Because you have to have that energy input, or there's no catalysis, you just have a decomposing compound. Since we did this, when we published the paper in Science, I just want to tell you that wasn't a technology paper, because people say the catalyst is too slow. It's not. In the last few months, which we aren't publishing yet because a company is formed to bring this to the port. I don't even own it anymore. I gave it all up to the computer people who you know. It's all their names on here, because I said if you did it with computers, please now do it with this. We've already been in SunCat been able to move this up by 200 times in activity. So that movie I showed you was 10 milliamps per centimeter squared. We're at 100 milliamps. And at 100 milliamps, we have stability now going for out of the Charles River 4 months, out of regular water over 8 months, because the catalyst is always healing itself. So there's a good technology. I just want to say this looks a lot like OEC. And OEC, both earth-abundant manganese, we have earth-abundant cobalt. You self-assemble, you have a tyrosine oxidation from a photon input in the PS2. Take manganese 2 to 3, and then this cube self-assembles. Here, we take cobalt-2 to cobalt-3 from the current of a photovoltaic, and then our cube self-assembles, either Holger's or our small modification. We have a repair mechanism. Because of that repair mechanism, we can use water. And even the metal and metal oxygen distances in both are the same. It turns out we now believe this is in a deep sea algae. It's cobalt, not manganese. Give me 9 more months, I think I'll have it now. Okay? And it's giving you most of the world's oxygen is from an algae called Prochlorococcus. Everything I've talked about is just oxygen. You still have to make hydrogen. In the original paper, we used platinum. But remember, we're in water, so I don't have corrosion problems to deal with. In the last few months, we've come up with a ternary alloy, 3 different metals in the right concoction. One of the metals gets dissolved out electrochemically to give high surface area, to give us a ternary alloy. One metal controls phosphate binding, make sure phosphate doesn't pass the surface. The other metal does the heavy lifting for hydrogen. I'll just tell, I can't, this is all getting patented by MIT. I'll just give you, this is one of the metals coming out, and then we hit the stable phase, which is forever. And I just want you to look at the numbers. 35 millivolt over potential out of regular water with phosphate at 1,000 milliamps per centimeter squared. That's way better than platinum in a fuel cell. So I think we have these are very, very cheap metals. We've been able to do that. So we can run the system like this with very cheap metals, photovoltaic input, water oxidation, and hydrogen reduction. You can also do this reaction. Remember, you just have to take cobalt 2 to 3, and then the catalyst forms. So you can take a photovoltaic material directly. Remember I told you about module costs? So let's get rid of the module now. Just get rid of it. Let's just use the semiconductor. So when you shine light on this, you make cobalt. The hole from the semiconductor, that takes cobalt 2 to 3, the catalyst forms, and then you can do water splitting. And the person who's shown, there's a bunch of people who have shown this now, Dan Gamlin at Washington. Here's the latest data. Lots of people in the world now have been working on this. I'll show you K.S. Choi from Purdue. She's the young inorganic chemist at Purdue. The reason why I like this is she did some very careful studies. This is tungsten oxide. You see it decaying. And you see when the catalyst goes on, it becomes stable. I'll be done in a second. I'm going to be really done in a second. So it becomes stable. I knew this. Okay, I'm going to be done in a second. And then seriously? And I'm taking water out of the O2, no hydrogen peroxide. So the beauty of this thing is it stabilizes the semiconductor so you can run direct. So here it works under ambient conditions, hydrogen self-healing, yay. I got rid of platinum. I can use any water source, so now I'm not only going to give energy to poor people, storage, but I can also give them clean drinking water, right? And so here's a commercial electrolyzer. I'll tell you right now, we're building electrolyzers by hand for only $28 versus $12,000. That's for 1,000. This is 100. They run a kilowatt, we run 100. Why do I like 100? 100 watts in 24 hours is 2.4 kilowatts. The average American uses 24 kilowatts. So at $28, I can make poor people 1/10 an American, since energy use scales with wealth. And it's because of chemistry and the self-healing mechanism. That means you can start thinking about high throughput manufacturing. So Mr. Tata in India, Rutan Tata, is hooking up with us. We're delivering him a prototype in the next 2 months, and he's going to start high throughput manufacturing for India. I'll tell you the way the catalyst works as is, even for an average American taking an 8 megawatt system, taking half of it, which is 6 by 5 square meters, 30 meters squared, I can generate enough, split enough water to store enough energy for you in America in 3.5 hours. People worry about hydrogen storage, don't. At 200 atmospheres, I can just put it in an aluminum tank and bury it outside. That's for an average American, that's 31 kilowatt hours. I only need 11 liters for poor people. So we're doing that right now. So you can start thinking like this, have a PV, send it to our cheap system, put it in an aluminum tank. The question still is, can I get a cheap enough fuel cell for the poor? So that's something we're working in partnership with. I'm ending. That's the amount of water you need to run an average American home. This house, this was a National Geographic. I calculated this guy's energy bill. I have to split that much water a day. I just went for the poor.